Okay, class, so we just learned that the fully corrected endurance limit, the endurance limit of a real part, can be approximated from the endurance limit of an ideal test specimen by multiplying by all these Marin factors. And the first Marin factor that we're going to study is K sub A. It is the Marin factor corresponding with the surface finish of the part. Here's a plot of the surface factor Ka as a function of the ultimate tensile strength of the material. So we have ultimate tensile strength in KSI on the horizontal axis, and on the vertical axis we'll have the surface factor K sub A. Suppose our part does have a mirror polish. Let's just make sure we understand this. What do you expect the surface factor Ka to be? How much will the endurance limit of the part be reduced compared to a perfect test specimen if the part has a mirror finish? So pause the video for a minute and think about it. If it's perfectly polished, just like a test specimen is, then the surface factor Ka will be 1 across the board. It doesn't matter what the ultimate tensile strength is. Compared to a perfect specimen, well, it has the same condition of a perfect specimen. If it has a mirror polish, then we do not need to reduce the endurance strength by any factor. But if, say, it were ground finish and it weren't a perfectly polished, then you'd get a different sort of curve. For a lower ultimate tensile strength material, it turns out you have a factor that's very close to 1. As the steel gets stronger and stronger, stronger steels tend to be a little bit more brittle, right? A little bit less forgiving of cracks, especially near the surface. And so if you have a ground finish, it's a little bit less pristine. You could have tiny micro cracks, little imperfections that turn into big cracks as you apply cyclic loads. They open up over time and eventually the whole material fails. And so that's why when you've got a less than perfect finish, then especially as you have a little bit less forgiving steel, you end up with a lower surface factor and a lower endurance limit as a result. If you have even worse conditions in your steel, if it's just machined, say like on the lathe, or if it's been cold drawn, if it's hot rolled, even lower. If it's just forged, then it's even worse, right? And so if you've got these really strong steels and the surface finish is really poor, you could end up with only 20% of the endurance limit that that same steel would have if it had a perfectly polished finish. So it's really important, if you need a good fatigue strength for your part, to make sure that the surface of the part is nice and shiny, because any imperfections from your manufacturing process cause cracks, and those cracks grow over time when it's subject to load, and that's what you want to avoid. So it turns out that these curves can all be approximated with a few constants. Our surface factor Ka is given by some A. This is different from that A. It's a constant times SUT, the ultimate tensile strength. It's a function of the ultimate tensile strength to the bth power, where A and B are given in table 6-2 of the Shigley book. So let's do an example. A steel that has an ultimate tensile strength, 150 KSI, undergoes a rotating beam fatigue test. And first we're going to estimate what is the endurance strength of a perfectly polished test specimen, SE prime. And then we're going to say, all right, considering that the surface might not be perfectly polished, let's say we forgot to polish our test specimen, what would we expect the endurance strength of a machined specimen to be? So here's just the information directly from the Shigley book. Let's write down a little bit of information about our problem. SUT for our problem, our steel, is 150 KSI. And the first thing that we wanted to know, what is SE prime? What is the endurance limit of a perfectly polished specimen? And all that we're given is the ultimate tensile strength of the steel. Now, we've already covered in earlier parts of the preparation that we can estimate the endurance limit of a perfectly polished specimen as 0.5 times the ultimate tensile strength of the material. So in our case, we have 75 KSI is what we'd expect our specimen to survive for an infinite number of cycles. That's the endurance limit of a perfectly polished specimen. That was the first part of the problem. And the second part was, what if it were machined but not polished? So we wanted to find out what is the endurance strength of our real part, which is really just a test specimen, but it's not polished. when we modify it by the surface factor Ka. And all these other factors that we could have, Kp, etc., these are all 1. Okay, because we have all the other conditions of a specimen except for the surface finish, times Se prime. And Ka is given by this equation here. Ka is equal to A ultimate tensile strength to the bth power, where A and B are given in this table. And we have a machined part, machined or cold drawn. You've got a different number that you need to put in here, whether you're talking about KSI or megapascals. For KSI, our factor A for machined or cold drawn is going to be 2.7. And we have our SUT, that is 150 KSI, to the bth power, where B is our exponent B. It doesn't matter whether we're talking about units of KSI or megapascals. Our exponent B for machined finish is negative 0.265. And we find 0.7156. So the endurance limit of our real part is going to be about 71.56%, is a way of thinking about it, of the endurance limit of a perfectly polished specimen. Just because we didn't polish it, we left it machined, we get a 30% reduction in its endurance limit. So we have 53.67 KSI. And we're going to have a bunch of other factors to keep in mind, right? If the temperature, the size, all these different things we said were 1 right now, for real parts, they're going to be less than 1. So we're going to end up with additional reductions in the strength of real parts.